Bit better?
A little bit. Okay. We're happy to have Diksha, who has a different title from the title she sent me.
What is
The new one is the one that you sent me is on the behavior of singular quadratic forms under purely inseparable extensions, and the new one is on
the abstract is still the same.
okay, the new one is on strict quasi-hyperbolicity of semi-singular quadratic forms. And it's important that we're reading practice.
Thank you, Alan, for the introduction. See, I thought writing again. This is a joint work with and with Lagrivi. And I'm thankful to both that I'm here today. And most important, throughout the talk, we'll work over fields of characteristic too. So whenever you start with other talks, when they start with fields of characteristic dot, usually the first thing they write is our form looks like something like a diagonal form we have today. You can still see. So something like this fails when we are working over fields of characteristic too, but we can still say something like that. We still know what our forms phi will look like. They will look like something like these blocks. What are these blocks? Each of this block is something like. And this part is what? Remember there is talk called the radical of phi. This part was what was called when the radical is 0, where we have just this part, that is that R is non-zero and S is 0. We got it non-singular. Then our S is 0, S is not 0, R is 0. This is totally similar, and when both of them are non-zero, it's nice because now whenever we have one question here, we have at least 3 questions here. Whenever we have a question that is same for quadratic and bilinear, right? Since there are no more analogous, we have 4 questions here. Great for a PhD student. You start your work, you already have 4 questions at hand. So, but yeah, rest of the things we can talk about in a similar manner. A form is isotropic, whenever we have a non-zero vector which represents 0. But now we can talk about something nicer. Here, it's just existence of such a vector which is 0. Now we can talk about whether the 0 is coming from the non-singular part, totally singular part, or somewhere this totally singular part is affecting the non-singular part. And hence, which makes us the need to differentiate between how these things are come out. So in that case, we have again, after we are already done talking about isotropy, we can still talk about with decomposition for these forms. We will split our phi into an isotropic part, whether the 0 is coming from blocks like this, or the zeros are coming from blocks like this. This is what we are going to call our bit index of phi. This is what we are going to call our defect index of phi. And whatever is the sum is what we are going to call total effects of phi. Basically counting the isotropy, but from different, from its contribution from different parts. So here, when we have isotropy, and we have something called maximum isotropy, is to call it hyperbolic, right? Whenever our form looks something like linear sums of these planes, we used to call phi to be hyperbolic. Now we need an extension of this notion, hyperbolicity here. I'm going to do the same thing. When we have a non-singular form, and it just looks something like hyperbolic planes of this form, which are nothing but xy, which means they represent everything. This is what we're gonna call our form is hyperbolic. A non-singular form that looks just as if some hyperbolic planes is hyperbolic. Now, when we're talking about maximum number of zeros coming, but they are not for non-singular forms, for totally singular forms, which means our form is going to look something like a lot of zeros. How many? At least half its dimension. When phi is totally singular, we are going to call it quasi-hyperbolic. When we have a semi-singular form, we can, since for semi-singular form we talked about total index, we say that it's going to be quasi-hyperbolic. A semi-singular is going to be quasi-hyperbolic when its total index is again more than half its dimension. But actually, we can talk something about the following. Because this quasi-hyperbolicity does not mention whether the zeros are coming from here or here. For example, we can talk about a form phi, say f t1, t2. This is a form defined over f with indeterminates t1 and t2. This form has total index 3. So this form is indeed quasi-hyperbolic, but its bit index is 0. So this creates a need to talk about that it has not just maximal total index, but its total index is coming contributed from both its parts, non-singular as well as totally singular. In this case, we felt the need to define strict quasi-hyperbolicity, which is trying to say that if I have a form phi, its bit index is maximal. What's the maximum bit index possible? It is dimension of phi minus dimension of its quasi-linear part. Let me mention that this part is what through the top I'm going to be calling quasi-linear part. So when its bit index is maximal, its defect index is maximal, I'm going to call the form to be strictly quasi-hyperbolic. So this example is clear. If a form phi is strictly quasi-hyperbolic, it is automatically also quasi-hyperbolic. But the vice versa is not true. If my phi is quasi-hyperbolic, like we have in this example, it need not be strictly quasi-hyperbolic. So it's nice. We have just one notion of hyperbolicity in characteristic, not true. And now we have hyperbolicity, quasi-hyperbolicity, strict quasi-hyperbolicity, quasi-hyperbolicity for totally singular forms or semi-singular forms.
So to make sure I follow, so in the strict quasi-hyperbolic case, you can choose a way of writing down the form in such a way that the non-singular part is hyperbolic.
Yes, exactly. So it's always saying that the non-singular part of this form is hyperbolic, and its totally singular part, its quasi-linear part is also quasi-hyperbolic. So its isotropic index is maximal. The cell that contribution is from both the parts, not just by one.
Okay, so that's why you can choose the way of writing that.
So what's nice thing about this quasi-linear part is it's unique, as he said. If we have phi, such that it has some non-singular part and some totally singular part. And same phi, this, and in this case, we know for a fact they'll also be isomeric. But this thing will not be true for R prime. A very nice example for this is if I have AB times A, this form is actually isometric to a hyperbolic plane times A. The two forms are not symmetric. So this quasi-linear part is nice. It's unique, and as I was mentioned in the last talk, we know something nice about the behavior of this form, which is even when we extend scalars, it comes from the base field. We extend scalars. So let's talk about what happens when. Now we know how form looks like. A quadratic form for a base field of characteristic 2 looks like this. We have so many properties to consider. So let's see about what are the properties. How do we know? First basic cases, whenever we have a quadratic form, if we extend it to a field extension, under what properties it would be isotropic, it would be hyperbolic. The first case we always consider is a quadratic extension. So the same that we have for characteristic. Now too, whenever form phi is hyperbolic over a quadratic extension, we know that phi is divisible by this form. The same result is also true here for quadratic extension. I'm going to keep coming back to these points of strict quasi-hyperbolicity, its quasi-linear part. Okay. So the same result that we have for characteristic not 2, we also have for characteristic 2. If we have any quadratic form phi, and we extend scalars to any quadratic extension, it is quasi-hyperbolic over f would be if and only if it is divisible by 1. What do we mean when we say it's divisible by 1? Simply, we can write our form phi as some suitable number. Both the parts, since it's quasi-hyperbolic, in this particular case, its non-singular part will be hyperbolic. Its quasi-linear part will also be quasi-hyperbolic. In this particular case, when it's just a quadratic extension, quasi-hyperbolicity and strict quasi-hyperbolicity are the same. So, what happens? Here, we just considered the question that if we have a quadratic form phi and we are extending its scalar to k, under what conditions phi k is hyperbolic? We can talk about phi k being hyperbolic whenever phi is non-singular, quasi-hyperbolic whenever phi is totally singular, and then we can ask about strict quasi-hyperbolicity whenever phi is singular. Now, we work over any arbitrary field extension, it's going to be hard. We're just going to talk about first this case when our phi k is hyperbolic. When our phi k is hyperbolic, that is, what do we know? For which field extension k over f do we know that for non-singular forms? For non-singular forms, phi k is hyperbolic. For these, there are a lot of results known in the literature. I don't remember the rest. I noted it down. So for quadratic and biquadratic extensions, whenever K is a quadratic or a biquadratic extension, this is known by Baiza in 1978. For biquadratic, purely inseparable, so the result by Baiza was for separable extensions. For biquadratic, purely inseparable extension, the result was by Mamon and Moresi in 1995. For simple, purely inseparable quartic extensions, the result was by Ahmad. For multi-quadratic extensions, the result is by Lefebvre. For quartic extensions, the result is by Hoffman and Soviet. And the latest in the literature, the one that you want to be interested in this topic, and this K by F is a purely inseparable extension. So in the case, when K by F is a purely inseparable extension, to Soviet, we know how these forms phi look whenever phi k is hyperbolic. For non-singular forms, this statement that phi k is hyperbolic is other words of computing the width kernel or the width group W2 by. The result that Soviet says is, in this case, our phi will look like it equivalent to some generator forms where there is GI some complex living structure u to the power di, d1, d1, and so on. Where what are these d's? It's a purely inseparable extension, then we can say our k is nothing but looks something like has some exponent and stuff. So 20, Soviet has given an explicit computation for non-singular forms. How do these non-singular forms look over hyperbolic extension? How these non-singular forms look over purely inseparable extensions, and they are hyperbolic. Next question automatically arises. If we know it for purely inseparable extensions for non-singular quadratic forms, how about totally singular forms? So now, in this direction, if rather than non-singular forms, we have phi totally singular, if we have phi totally singular, we want to say, see, where it is quasi-hyperbolic over K. Before I come to this, I'm going to recall a result by Hoffman, which doesn't talk about quasi-hyperbolicity but about isotropy, and says if phi is isotropic over K, but K is not just any purely inseparable extension. In addition to purely inseparable, it's also modular. If my K is again f of 2n1 d1 minus ds, then I can also associate to this a Pfister form phi, which is phi d1 up to ds. So what Hoffman states is, if phi is isotropic over such a modular purely inseparable extension, this can happen if and only if is also isotropic. So we have this, we do know how these forms, totally singular forms, behave over purely inseparable extensions, but sadly not just any purely inseparable extension we know for modular in case of isotropy. Naturally, what we try to do is, we try to extend this isotropy to quasi-hyperbolicity, which brings us to the first result we're going to talk about here. Okay. So here, keeping this rest of the condition same, we have phi k is quasi-hyperbolic when phi is totally singular, if and only if phi times kf is quasi. We extend this result of Hoffman from isotropy to quasi-hyperbolicity using this plus the property that our Fisher forms are round, count the number of zeros and extend the argument. So the next thing is, now we know how our forms, non-singular forms and totally singular forms behave when extended to purely inseparable and purely inseparable modular extensions. Very natural thing now to ask is, what do we say about semi-singular forms? Recall. Semi-singular forms are the ones which have the non-singular part as well as the totally singular parts. So extending the same question that we already know for non-singular forms and totally singular forms, we ask if we have a semi-singular forms, by again anisotropic, under which conditions phi k is strictly quasi-hyperbolic. So strictly quasi-hyperbolic means it has maximal bit index as well as its quasi-linear part is also quasi-hyperbolic. You know the answer independently, right? A very natural choice is that we club the two together and put it together. So you can say it will be strictly quasi-hyperbolic if its bit index, or the definition is strictly quasi-hyperbolic if its non-singular part comes from something that Soviet has already given when a non-singular form is called hyperbolic. So if its non-singular part comes from the bit kernel of KFF and Qn of phi is quasi-hyperbolic, the condition is phi times KF is quasi-hyperbolic. I'm just using a very genuine choice that we have, that we know when non-singular forms are hyperbolic over these extensions, we know how totally singular forms are over modular extensions. So taking the two together only for modular, because we're taking the result from here, saying that for some same semi-singular forms, we predict that its behavior will look bit equivalent to its non-singular part coming from its bit kernel and it's totally singular part such that the totally singular part is quasi-hyperbolic if and only if phi k times QL phi is also quasi-hyperbolic. Which is what our aim is going to be. Let me just rewrite this theorem in a more formal manner. So let phi be an anisotropic semi-singular quadratic form. My K is a purely inseparable modular extension. Then the following are equivalent. First, phi k is strictly quasi-hyperbolic. And secondly, phi is bit equivalent to some non-singular part and its quasi-linear part such that its non-singular part comes from the bit kernel W2KF, which has been computed in Soviet, and the condition on quasi-hyperbolicity of quasi-linear part, which we have extended from the result of Hoffman, that this times phi KF. What is again recalling with what is phi? Phi is the quadratic Fisher form associated to the purely inseparable extension. So this is quasi-hyperbolic. Now one can ask, If we already have the result for non-singular forms and totally singular forms, why is it difficult to prove it for semi-singular forms? Reason? It's very simple, like we just talked about. My AB times A. So when the two are coming together, non-singular forms cannot behave independently. So even though we know very well how non-singular forms get when they are alone and hyperbolic, if they are coming with the totally singular forms, we can't use the same behavior. So we need to use a very different approach. Let's see. So the approach that Soviets used to prove only for non-singular forms is moving first to differential forms. The result that I mentioned in his last slide, that you have a one-to-one analog between non-singular quadratic forms and differential forms. So we see the kernel for differential forms and then compute how the forms will look there and then come back here in this. Such an analog is not known for semi-singular forms, so we can't use the technique here. This, again, we can't really do because this just uses the roundness of the fixture forms and the fact that it's isomorphic. Note that here it's for modular extension. We can't really extend it to any other because for non-modular, pi times phi is always going to be quasi-hyperbolic, independent of the fact whether pi is quasi-hyperbolic. So here, this modularity indeed is important and we can't be true. So what do we do for that to prove it in general? We use a different approach, extremely different approach. So to prove that, I'm going to first prove something. Different. So here, the question is that it's strictly quasi-hyperbolic. We call that the strictly quasi-hyperbolic meant that its non-singular part is hyperbolic, which means it has maximal bit index, and its quasi-linear part is also quasi-hyperbolic. So we're just going to concentrate right now on a form which is not strictly quasi-hyperbolic, but has a maximal bit index, and see if for that we can rewrite such a statement. And indeed we can. So the statement uses let phi be an isotropic semi-singular quadratic form. Again, here is the same purely inseparable. This time, I'm going to let just a purely inseparable extension and not modular, because I'm not going to talk about quasi-linear part at all. So then again, the following two statements are equivalent. First, phi as maximal bit index over k, and phi is bit equivalent to phi times QL phi, where phi again comes from this bit kernel which has already been computed. See, we're restricting ourselves to purely inseparable extension, not modular, because that condition is only on the bit index part. We do not care about quasi-linear part. We need the modularity when we need the quasi-linear part to also be quasi-linear. So we are gonna, our goal is going to prove this in order to reach their parameters. To prove this, I'm just going to use 5 rules. We're going to write that in the corner, and following the proof, see that I'm not really going to use anything from outside those 5 rules from the literature. So this is just for that the result that we already know for totally singular part. What is this? So what are the 5 things that I'm going to use? First is, we talk about how the quasi-linear part of a form is unique and how it's nice that it is for totally singular forms, all the field extensions are excellent. That is, every time I talk about phi, totally singular, and I talk about any field extension K over F. Any field extension K over F, anisotropic part is always defined over F. That is, you can always find suitable scalars C1 up to Ct such that for every field extension, anisotropic part looks like these scalars coming from base field F. So, every field extension is excellent for totally singular quadratic forms. Very strong, very nice. Second, bit cancellation. Bit cancellation more or less works in a similar way that it did in characteristic law 2. But here, we can cancel all the zeros that come from the totally singular part, or we can cancel any non-singular form. Not totally singular form because it keeps altering the behavior. For example, again, favorite example, A, B, A, hyperbolic A, can't cancel it. So next thing that we are going to use is 1, 2, totally singular forms. Any field extension is excellent for totally singular forms with cancellation. Third, some basic identities such that squaring this part doesn't change our quadratic form. Something like this. We can play around with this. Okay, this completion lemma. What does completion lemma says? If I have two forms, R, non-singular forms R and R prime, such that R times C1 up to CS is with isometric to R prime times C1 prime up to CS prime. We can complete this totally singular form with suitable scalars such that this is R times B1. We can basically complete the totally singular part back to some non-singular form. And last, and full and final, is a small identity due to error variant biasa for n is equal to 2, which could easily be extended to bigger n, which is when we have a fixture form that looks like and A is A1 plus A2, then this form is with equivalent to 1 A1 times 1 A1C by A, 1 A2 times 1 A2C by A. And A is A1 plus A2. I know these 6 conditions here. As I move towards this proof, I'm just going to take tick mark that other than these 6 conditions, we won't use anything to know what the structure would look like whenever my form phi has a maximum vertex over K. So let's go. Now, to prove this, as I said, that the problem occurs for semi-singular forms is that its totally singular parts keeps on affecting the non-singular part. So we split the proof into 2 parts to make it easy to handle. We split it into 2 parts. First step, we assume that we do not have a variable totally singular part to handle, and phi is of type 1s. We call what is type, as I have said in this last talk, whenever our phi has these blocks A1, B1, AR, BR, even up to CS, the type is RS. So we have phi of type 1s. So up to a scalar, we can write as phi 1b and some scalars in the totalistic part. Now, here 2 implies 1 is automatically true because if it's in the width kernel, it has a maximal width index. So we are note that we are just proving for 1 implies 2 because 2 implies 1 is like this. To stop when if phi looks something like this and we are approaching 1 implies 2, then by our hypothesis, we have phi k to be nothing but a hyperbolic plane times some suitable scalar C1 up to Ct and some numbers of yes. All these scalars C1 up to Ct could be chosen over the base field F. This is the first one, right? So if we have this, how many zeros we have? Just S minus 2 number of zeros. So I just write this. This is going to be my 1b C1 up to Ct S minus t number of zeros, and using the second bit cancellation, you can cancel zeros. We are left with 1b C1 up to Ct extended to k is a hyperbolic plane times C1 up to. On the right side, we have hyperbolic plane, simply trying to say that this form over k is isotropic. So we get is 1b times C1 up to Ct is isotropic over k. K is a purely inseparable extension. Just the form 1b cannot be isotropic over it. Therefore, for this form to be isotropic, there should exist a scalar C such that C belongs to dk of 1b as well as dk of C1 up to C. Simply using the fact that it's isotropic and just a non-singular block of dimension 2 cannot be isotropic over a purely inseparable extension, we have that there should exist a common scalar that's represented by this part as well as this part. So I can write as RC as Ci xi square I going from 1 to t. We have a very nice choice of C, and we are going to see now what we can do with this choice of C. So with this choice, we're going to construct a quadratic fixture form. Which quadratic fixture form are you going to construct? This is going to be 1C times 1. Now C is summation of Ci xi. 1 Ci xi. We can play around with this using this final one, this identity using Aravari and Diagram. And if we do this, we have this looking something like this is big equivalent to summation 1 Ci xi. Correct? Just use this identity over these scalars, and these xi's are coming from k.
Square. Ci xi square.
Now, this is a bilinear form. We can remove these xi squares. With this part, we can use this identity 1a is isometric to 1a square. So we can choose a very nice number n such that this is bit equivalent to I going from 1 to t 1 Ci times 1 ci xi squared d by c, such that this is the L is such that these indices is a very big number such that all these indices raised to the power 2L belongs to F for all time. Now we can write each of this number to be a BI, and we have our 1C to be bit equivalent to the Pfister form CI BI, where both these CIs and BIs are over F. Right? Why are we interested in this form? Because we can write this CI BI to be our form phi, which so you can say this is a very nice form phi. Then we'll let our phi to be the sum of these forms CI BI. Why are these so nice? Because all these forms that appear here, that is CI, CIXS will be by C, is actually at the same generators that Sobiech got when he computed the non-singular form, the pit kernel form and so on. So the thing for which he had to go through differential forms and come back and make some computation, they naturally appeared here just with a nice choice of CIs and XIs. So we use this, we use this. Did we use this so far? Maybe not yet. We haven't used this. 4 and 5 we haven't used. We have used first, second, third, and sixth. I'm going to remove this because these are all the tools we're going to use. We have a very nice choice of 5, which is we're letting our 5 to be CI BI. Now what we needed was this 5 should have belonged to the bit kernel of K by F. That's one thing we are yet to verify, that indeed that 5 belongs to this bit kernel of K by F. And it does, right? Because our summations CI BI over K is bit equivalent to C and B. This form actually is nothing but 1B C1B. This form over K by a choice is isotropic. Right? Since 1B C1 up to CS is isotropic, we know for a fact this form is isotropic. Being a Pfister form, it's hyperbolic. Therefore, this form indeed belongs to now, last step, that is, we should get that our phi should be psi times this. And I'm extending scalars to K, I should be able to get back my 1B even up to C2. Right? Now at that, all we need to do is when we have CI BI and we are having a sum with CI, this, we are going to use this identity. Finally, that was. Then we have 1B B1 plus B2. This is bit equivalent to 1B1 1B. So to do this, whenever we have psi plus C1 up to Ci, we can write it as, once again, maybe a little. So let me, I have my psi to be this form CI BI. I have we have made sure that psi actually belongs to the bit kernel of Q by F. All we are left is to make sure that this form psi times C1 up to Cs is actually bit equivalent to our original form phi, which was nothing but 1b C1 up to Cs. This is the only step we are left to be sure about. Yeah. See that? First thing we notice is that our Di's, when we take summation of Di's were Ci d xi squared b over c, all these terms. So this is to the power 2n summation I going from 1 to n. Yeah. When I take the sum over this, we'll have these terms. Some of them is again c, so this is b to the power 2n. Again, repeatedly using this identity, 1a is same as 1a squared. This is nothing but b. So summation bi's are nothing but b. Now we have this form ci vi with each of these terms c up to cs. If I'm going to take the sum of them, if I'm going to take the sum of ci vi's, which each of ci, this is nothing but 1 bi ci, right? That is nothing but 1 bi ci 1 bi times ci. This part is indeed isotropic, so we are left with 1 bi ci. So then I'm going to apply summation of ci bi times ci. We will have summation of 1 bi times, we'll retrieve back our quasi-linear part, and summation of 1 bi using the other identity I wrote is nothing but 1 summation bi with equivalent to this, and this is nothing but that b. So when we verify that our phi is nothing but the same form 1b c1 to cs. The original choice that we needed are phi to be x. Sorry for the messy calculation. So here I see this is a very clever choice of CIs and BIs. BIs are appearing same as this are the ones that same as they appear in the generators calculated by Soviet for non-singular forms. And indeed for maximal weight index, we have that it has maximal weight index if and only if its non-singular part comes from its vector. Note that here we did not even have to take the modularity condition because we just worked over the singular part. But here this was of type 1s. Now we still need to work whenever we have a non-singular part of a bigger dimension. So in the second case, when we have a phi to be of type Rs, we'll try to use induction over R. We'll try to use some argument that we reduce our form to a dimension of 1 less R minus 1s, and then use the induction. To do that, suppose here we have phi to be P1, P1, AR, dr, C1 up to Cs, we'll add a very nice suitable form, which is A1, A2 up to AR. When we do that, this form phi will be nothing but phi times A2 to AR will be nothing but A1, B1. Each of these block A2, B2 with A1 will become a hyperbolic plane. So we'll have R minus 1 hyperbolic planes time E1 up to CS. A2 up to A1. Since this is now a block of non-singular part of dimension 1, 2, we can use our first one and write. When I will do this computation, I'll be left with something that looks like E1 C1 times A2 AR quasi-linear part of phi looks like some suitable form that appeared in the part A, and might have missed some hyperbolic planes, let me be sure. Sorry. Yeah. When I will extend this to k, our phi will be go to 0, and indeed since it has the maximum vector index. So now again we can add back all our these A2 to AR with suitable scalars using the completion lemma. On the left side we'll complete by B2 up to BR, and here we'll have something like some blocks B2 prime, AR prime, BR prime, QL prime. When we'll extend this to K, this will go to 0. This again has maximal bit index. Now, but this is of dimension less than R. And we proceed to find out. So we have something. In the same case, we know how our phi looks like whenever it has maximal bit index over any purely inseparable extension. What does it look like? It looks like a non-singular part that's coming from its equal. Now, to go from here to here is pretty straightforward. One part just follows the definition. If it is indeed strictly quasi-hyperbolic, the definition is it has maximal bit index. Using this result of maximal bit index, we know it is bit equivalent to phi times Q alpha. Since it's strictly quasi-hyperbolic, a quasi-linear part is also quasi-hyperbolic, for which we extended the result of Hoffman, and that says that which means phi times Q alpha is quasi-hyperbolic. Or vice versa, if we have something like this comes from bit kernel automatically, it has maximal bit index, and it's quasi-hyperbolic, so following the definition, it is strictly quasi. In a nutshell, what we tried to do was break it into two parts and approach, because non-singular part is the one with the problem. We approach it when non-singular part is a very small dimension and we can tackle it, and then extend it using this argument to mention. A very small application I want to tell right now, I just stated is, once we have this, we have try to use this result whenever we know if we have a phi, a semi-singular form whose bit index we know is something like f. In this case, we try to give a result at how this phi will look like. It will look like bit equivalent to some form psi. Again, it comes from the bit kernel. Some very nice forms I going from R to M of blocks of 2, which are again defined over the base field L and 2. So now what we're trying to do is, now that we know how our behavior of semi-singular forms is over purely inseparable extensions, in this case only modular. Here, since we're only talking about the bit index, again, we need not consider modular, and we are trying to know how our forms look like. That's all. Sorry for the messy calculations. But I just want you to do the calculations to see that we are not using anything from out of it. Everything on the board, and we have the results. Something very strong that we know how our form looks like. Well,
Questions? In Zubir's paper, and also I think in some of Ahmed's earlier papers, they are also trying to consider in addition to those purely inseparable extensions, also extensions with additional quadratic separable bit. We try to.
Not that, but we tried something different. We rather than working over like just extensions purely inseparable, adding separable part, we did try to work over some special polynomials. Polynomials that look something like a1 x1 square, an x1 square plus x4. Then that represents something. Under what conditions they become isotropic over something. So we're trying to extending not just to purely inseparable, but function fields of some special type of polynomials, but using similar kind of skills, not something from outside. The Soviet paper becomes like you have to just using Karp's formula, a lot of heavy results. This is why trying to keep it self-complete by not using much tools from outside.
It's actually quite nice that you managed to avoid all the things that naturally would use cohomology for, but you cannot use them. Totally similar.
What was interesting was when we were doing the calculation for this, the forms that appear C, I, B, I's, they are of the same form that Soviets had using differential forms.
When you add one separable slot, even for the type of cohomology situation, because very hard, instead of taking an arbitrary remove a popular purely separable extension, okay, just quadratic one simple quadratic, and you add separable slots. That is very hard to do. And you can, for example, if you add separable slot, you can't use the same argument because Diksha, as she explained a few minutes ago, and sometimes you will use the excellence of purely inseparable multi-quadratic extension. When you add separable slots, we don't know that it is excellent or not.
Yeah, one of the crucial every time is that all these CIs up to CTs, we can always take them over the base field.
But here, for example, as Diksha explains, the nice application at the end. When the bit index is at least n, you can give criterion when this situation happens. You can do it for other extensions. It's very special for pure inset.
That's part of the miracles of calculus. Any more questions? So let's thank the speaker again. Thank you guys for coming. Thanks for the other. Masha? Thanks.